Let's take a trip to Newton's Mountain. Don't call your travel agent. Don't log on to Expedia or Travelocity. Newton's Mountain is a place we journey to in our mind. And as you know, Newton's Mountain is a thought experiment for us to try to figure out exactly how fast something would have to be projected in order to remain in orbit around the Earth. If Newton's Mountain really existed, it would be a great way for bored people to play catch with themselves. You could climb to the top of Newton's Mountain, figure not drawn to scale, and then throw a baseball. And if you throw it too slow, it crashes into the Earth. Throw it a little faster, it still crashes into the Earth. But if you could throw it just right, then it would fall, but not so much fall into the Earth, but rather fall around the Earth. If you throw it any faster than this, and it might still orbit the Earth, but instead of a circular orbit, it might go in an elliptical orbit. For the elliptical orbit, there's a name for this distance at which the baseball would be farthest from the center of the Earth. We would refer to this as apogee. G, like geology or geography, to remind us of Earth, and ap, meaning far away. So the farthest point from the Earth is apogee, and then in the same way, when it comes back to your hand, then it's at its nearest distance from the center of the Earth, and is referred to as perigee. But we're not interested for now in the elliptical orbit. We'll get to that later in this unit. For now, we want to consider exactly how fast did the baseball have to be projected. In other words, with what tangential velocity does it have to be thrown to produce this circular orbit? So, all we need to do is consider that in a circular path, the velocity vector is always pointing tangent to the displacement, and the force is always perpendicular to the velocity. The force points straight toward the center of the Earth, so in this way, it's a centripetal force. Now, centripetal force is not a force in and of itself. Something always must provide a centripetal force, and of course, in this case, the force of gravity is what provides the centripetal force. So now we know how to find the magnitude of a gravitational force. It's G times the mass of the baseball times the mass of the Earth divided by the distance between the two squared. And as I say, this is not a scale drawing. So the distance, even if Newton's Mountain is several thousand meters tall, that distance pales in comparison to the 4,000-mile radius of the Earth. So for all practical purposes, the distance from the thrower's belly button to the Earth's belly button is nothing more than the radius of the Earth. So G times the mass of the projectile times the mass of the Earth divided by the radius of the Earth squared has to be equal to centripetal force, which is the mass of the object that's moving in the circle, that's the mass of the projectile, multiplied by its tangential velocity squared, divided by the radius of the circle, which is the radius of the Earth. Isn't that right? mv squared over r is the way we calculate centripetal force. So you notice, it doesn't matter whether you try to throw a baseball or shoot a gun and try to project a bullet, the mass of the object that orbits the Earth in a circle cancels out. One of the r's cancels out on both sides of the equation, and so we're left in step 3 with an expression that says the gravitational constant times the mass of the Earth divided by the radius of the Earth is equal to the velocity squared, so we get our result. The speed would have to be the square root of gm over r. Now, if Newton's Mountain extended beyond the Earth's atmosphere, you could get to a distance that's great enough that the object now represents a satellite that permanently remains in orbit. There's a lot of reasons why this is just a thought experiment. For one thing, this velocity, if we work it out, if we plug in the known values, let's express this. G is 6.67 times 10 to the negative 11th, but mass is very large. It's 6 times 10 to the 24th. Remember, this is the mass of the Earth, not the mass of the projectile. And then divided by r, which is 6.4 times 10 to the 6. I should put the units in, shouldn't I? This is 6 times 10 to the 24th kilograms. This is 6.4 times 10 to the 6 meters. And the units for the gravitational constant are Newton meter squared per kilogram squared. Okay, so before you grab your calculators and work it out, spoiler alert, this is a pretty large velocity. So large that there would be such a tremendous amount of drag force acting on the projectile that it would burst into flames. It would burn up, and certainly nobody's strong enough to throw something this fast. So this represents the lowest possible orbit. We're talking about something that's just barely above the surface of the Earth. Maybe Newton's mountain should be called Newton's hill. And the reason we have to picture a hill is we hope that it's tall enough so that the baseball clears the tops of the trees and the tops of the buildings and the top of your house and so on. So the lowest possible orbit is sometimes referred to as a treetop orbit. And for a treetop orbit, we're just saying that the radius of the circular path is, for all practical purposes, nothing more than the radius of the planet itself. However, you could have a projectile, and we have plenty of projectiles there. All of the satellites that are orbiting as we speak orbit at a distance that's well above the surface of the Earth, such that r is greater than r. And in that case, it would still be the same formula. The speed would be the square root of gm over little r, and this r as a variable could be any value. And so the idea is, since there's an inverse proportionality, the speed of a satellite would be inversely proportional to the square root of the distance. The farther away a satellite gets, the smaller its tangential velocity in its circular orbit. But for the case of the treetop orbit, the value of r is nothing more than the radius of the Earth itself. So now's the time to grab the calculator and see what you get. 6.67 times 10 to the negative 11th multiplied by 6 times 10 to the 24th kilograms divided by the radius of the Earth, 6.4 times 10 to the 6 meters, gives you a large number. Don't forget, you got to take the square root, and you should get V is about 7,900. Now, what are the units? Okay, let's see. We've got a kilogram, and that's going to cancel one of the kilograms. Meter, I'm going to cancel one of these meters. So we're left with Newton meters per kilogram, but a Newton is a kilogram meter per second squared. So now we have kilogram meters times meters per kilogram, right? Kilogram meter per second squared, that's the Newton, times meters per kilogram. So now we have kilograms canceled out. We're left with meters squared per second squared, but we're taking the square root of all this. So yeah, indeed, this does work out to be 7,900 meters per second. That's how fast something would have to be projected near the surface of the Earth in order to never crash into the Earth's surface, but instead maintain a circular orbit. It's a fantasy to think we can ever get this, because a treetop orbit, by definition, by being just barely above the treetops, is within the atmosphere, and the drag forces would cause it to burn up. But there are plenty of planets and moons in our solar system that have no atmosphere, and achieving a treetop orbit is entirely possible, although I think on all those other moons and planets there are no such thing as trees, so maybe a treetop orbit is not the best name, but for whatever reason, that's what we choose to call it. Now, this hints at exactly what the Earth's curvature happens to be. I want to remind you, if you were to stand on top of a tower and drop a rock or a ball or any object, there's a question, how far will it fall in 1 second? And The untrained physics students answers really quickly, oh, well, I know g is 9.8 meters per second squared, so in 1 second, the object falls a distance of 9.8 meters. When you first let go of something, its initial velocity is 0. To accelerate at 9.8 meters per second squared is maybe better thought of as increasing your speed at a rate of 9.8 meters per second. So after 1 second, the object will be traveling no longer with a speed of 0, but with a speed of 9.8 meters per second. So let's look at the average. If you start out with a velocity of 0 and uniformly accelerate to a velocity of 9.8, that means your average velocity was 4.9 meters per second. And if you average 4.9 meters per second for 1 second, right, the distance would be 4.9 meters. So here's the thing. If an object wants to fall 4.9 meters in 1 second, and an object that represents a treetop satellite is projected with a speed of 7,900 meters per second horizontally, in 1 second, the object wants to travel horizontally a distance of 7,900 meters. But it would want to fall toward the center of the Earth a distance of 4.9 meters. So when you look out over the horizon of the Earth, and maybe you're looking out over the ocean and you can see a boat sailing away, and you still see it sail, and then it sinks lower over the horizon as it sails away, and now this sail drops out of your line of sight. That's because the Earth curves away underneath, and for every 7,900 meters horizontally, the Earth drops down a distance of 4.9 meters. 7,900 meters, that's 7.9 kilometer, and 7.9 kilometers is about the same thing as 5 miles. So for every 5 miles out across the horizon, the Earth drops 4.9 meters, and 4.9 meters is about the same thing as 16 feet. So the Earth sinks 16 feet for every 5 miles outward. So there you have it. Just a little insight into Newton's mountain and treetop orbits. I think I have another video following this one that you can watch that will link you to a website where you can actually make Newton's mountain more of an actual experiment as opposed to just a thought experiment. Thanks for watching.